This is Professor Hui. Today we're going to explain the electric current. The unit for the electric current is the ampere. And what is an ampere? Now recall we defined earlier the electric charge with the unit of coulomb, whereby 1 coulomb is equal to 6.24 times 10 to the 18 electrons. So in a sense, the ampere, which is the unit for current, is equal to 1 coulomb per second. Effectively, if you have a wire, the current I is equal to 1 ampere if there are 6.24 times 10 to the 18 of these electrons going through a point in the wire in 1 second. And that's the definition that we are adopting in 2015 as a unit for electric current. Now, before 2015, the ampere is defined not so much by the number of electrons, but by the amount of force two electric wire would experience when a current of 1 ampere flowing in this direction and another current of 1 ampere flowing in the opposite direction, they will create an electromagnetic field, and this opposing current will push the two wires apart, and over a distance of 1 meter, if these two wires are also separated by 1 meter, then you will have an opposing force F of 1 times 10 to the minus 7 Newton. It's a very weak force that we're going to demonstrate through the following experiment. I hope in the experiment you saw that these two copper tubes move slightly apart when I turn the current on. Let me explain a little bit of the experimental setting here. We have 6 volts of lithium-ion batteries, for which we have wires running through these things, and the resistance of the wire is roughly 3 ohm. And therefore you can calculate, as we show here, that there is a current flow of about 2 ampere. And therefore you can calculate the amount of force that is experienced by these two bars, which is, if you assume that roughly we have 1 centimeter separation between the metal bar, then would experience over a distance of 1 meter a force of 1 dyne, which is 10 to the minus 4 Newton. That's a very, very weak force. So that's why you barely can see the movement. Now, in order for us to see more clearly how the electric current can generate a magnetic field, we have wound up about 50 turns of the copper wire, and we're routing through it about 1 ampere of current through these coils. And what we're going to do is that basically you see that we can show that there's a compass here, and if we push the button, you will see the magnet will shoot out. So this is a rare earth magnet with the south pole on the other side. And so when the current goes through the magnetic coil and create a south pole also here, this is an electromagnet and this is a rare earth magnet, they will push each other off. And therefore it would produce an effect that is very much like a magnetic railgun. Now in the next video we're going to explain the magnetic railgun, and it's very simple as I explain it. A magnetic railgun is very similar to the experiment we have here. What we have is that we're going to drive a huge amount of current up this rail and then return it back on the other rail. But instead of having this wire allowing the magnet to return, allowing the current to return, what we're going to do is basically we have a metal slug that can ride along the rail, providing a return path of the current through the magnetic slug on the other side. So what you see is that basically a very powerful current of more than 1000 ampere will create a very strong magnetic field that would push these two bars apart. But because these two bars are fixed in place, the only thing that can move is really the magnetic slug, and will push it out at very high velocity. In this video, we're going to show a world record-breaking magnetic railgun that produced in one burst about 33 megajoules of energy onto a single magnetic slug. Here we have the magnetic railgun. The slug traveling almost 6 times the speed of sound, slamming into an object. Creating a terminal velocity that is so powerful that it would just destroy anything in the pathway. Today we're going to design a magnetic railgun such that we can send goods of a mass of 200 kilograms to Earth orbit. Now, from basic physics, we know that we would need to shoot the goods at a velocity of 10 kilometers per second in order for it to reach Earth orbit and stay in the orbit. Now, let me give you a few more parameters. We are supposed to design a railgun that delivers an energy of 10 gigajoule, which is 10 to the 10 joules of energy, to impart that into the 200 kilogram. Also, we're going to do it through a current that is 10 mega ampere, which is 10 to the 7 ampere of current. And that's a very massive current. At home, most of your current switches are only 20 amperes. Also, we're going to look at the magnetic railgun, whereby the current is going to go down. This current of 10 to the 7 ampere is going to go down the rail that is going to be coming down through this magnetic slug back in this direction. So the magnetic field actually is on the inside going up, and therefore it pushes the 200 kilogram in this direction to achieve what I hope would be a 10 kilometer per second velocity. All right, so let's say the length of this railgun is of a length of 1,000 meters or 1 kilometer long. And let's just also assume that it takes a time of, for the slug to come out, it takes 1 second for the slug to travel from this end to the other end to achieve that terminal velocity. Okay? So another parameter is the separation of this magnetic rail is going to be a distance of 0.1 meter. So basically 10 centimeters. We're going to do some back of the envelope calculation for this magnetic railgun. The first question we're going to ask is, what is the power of the magnetic railgun? Given the fact that P is equal to the amount of energy, which is 10 to the 10 joule, divided by the time, which is 1 second. Therefore, we have 10 to the 10 joule divided by 1 second, and that's equal to 10 gigawatt. That is substantially bigger than the 1.21 gigawatt that Back to the Future required. The second question we're going to ask is the voltage. As we know that V is equal to P divided by I, and the fact that P, in this case here, is 10 to the 10 watt, and the current is 10 to the 7 ampere, that would give us a voltage of 1000 volt or 1 kilovolt. The third question we want to calculate is the force. Now, we're just assuming that the force experienced by these two rails, which is pushing it apart, is entirely experienced by this slug. So if you think about the force on the two rail, as we have seen before, F would be equal to, in this case here, a length of 1000 meter. And then what we have is basically a force that is created by 10 to the 7 ampere and of current. And we know that for the rail to be separated by 0.1 meter, and we need to square this because the force increases inversely as a square of the separation of the rails. And we know that if we have 1 ampere of current flowing through the two rails for a distance of 1 meter separated by 1 meter, we have 10 to the minus 7 Newton of force experience. So in the calculation, you would basically get an answer. This 10 to the 7 cancels out each other. You have 10 to the 3 and 10 to the 2, basically 10 to the 5th Newton. And that's a very significant force because we only have about 200 kilogram, and therefore the acceleration could be in terms of 1,000 meter per second squared. The fourth thing and the last thing that we can calculate is the velocity. Now here we're going to assume, just for the sake of rough estimate, that the velocity v carries an energy which is 1/2 of mv squared, and that's equal to the total amount of energy that is imparted, which is 10 to the 10 joule. So you do a very simple calculation. What you have, this is 1/2 of 200 kilogram, and the velocity square, which we don't know, is equal to 10 to the 10 joule. All right, so what you have is basically v squared is equal to the 10 to the 8, and you take the square root of that, meter per second, and that's roughly equal to 10 to the 4 meter per second, and that's equal to 10 kilometer per second, which in this back of envelope calculation reach the orbital velocity required, which is that you need to shoot the object at a speed of 10 kilometers per second.